This computer. Okay, welcome back to Chemistry 2341. It seems that everybody got into the exam and took the exam pretty well. There was only a couple little issues. I think everybody eventually got in, so that's great. And then that's why we do the mock exams, to make sure that everything's working and everything's going on. So we did have a little bit of hustle at the end there for a couple people, but I think everybody got in and got to take it. You'll notice the curved score is on Canvas. Don't worry about the raw scores. The raw scores on, I'm actually considering just hiding the raw scores on on Top Hat, because some of them are curved, some of them are changed. For example, the number 2 homework was erroneously assigned 40 points instead of 20 points. And so you'll notice when you go to Canvas, that has changed to a 20-point scale. It's the percentage that you had before, but it's on a 20-point scale, so all the homeworks are assigned the same. So I apologize for any confusion that might have had. So let me go ahead and review what's due this week. We're going to do Module 5 this week. It's going to be all week, and it's going to culminate in a student activity on Friday. The student activity on Friday is specifically looking at R and S and assigning those things as groups. And so that we're going to learn all about stereochemistry and the chiral carbons, etc. this week, and we're going to apply them to that group activity on Friday. There's a PDF copy of these slides on Canvas, and as well as there is a PowerPoint copy of these slides on Top Hat for review. Obviously, our Zoom class is going to be all 3 days this week because we don't have any exams or anything like that. And the second half of our class on Friday will be that breakout session where we can do those group activities. The homework for Module 5 will be due Friday at midnight. The Module 5 homework's a little different this week, okay? What I wanted to do is I wanted to try something to see if you guys like it or not. What I made is the reading assignment questions are the homework. You'll have 2 chances to get it right, and then you'll be graded. So it's the reading assignment that's your homework, and then I will release another set of 20 questions as backup, okay? So it's the reading assignment is the graded portion, and the backup is just going to be for your review to see if you're getting things right. Okay, so I'm kind of reversing the order of what I did last time to see if that's working. I've had some, people saying, well, I need more questions or I need more things. And so I thought I would do this instead. So we'll try it out this week, and I want to get your feedback on it next week to see if that worked for it. Okay, I'll answer the question in the Zoom chat later if you don't mind. Okay, so that means that our homework is the reading assignment, and it is due on Friday, and we have that group example on Friday. Any questions about what's going to happen this week? Okay, nothing on that. Okay, so I will go ahead and start sharing my screen with our newest chapter. Let's see if that's going to work here. And I know I don't like changing things mid-semester, but I think this will actually reward you for reading through the book. The book does some different things than I do, and so by reinforcing the book and me together should give you a very clear, understanding of the topics. And so I want to try this out for a couple weeks and see how that works, and then we'll move on from there. But I don't want to change too many things at once, but this is the one thing I want to change this week. Okay, so today we're going to talk about stereochemistry, okay? And so the idea here is that stereo actually means 3 dimensions, okay? So stereochemistry means that we have something that's defined in 3 dimensions, and therefore they have fixed in space positions of atoms, okay? So if we have fixed in space position of atoms, then we have an opportunity to have the same atoms hooked together almost the exact same way, but have a slightly different space, slightly different position in 3-dimensional space. And that's what we're talking about here, okay? So the first thing I want to talk about is isomers, because again, you can have isomers are things that are different compounds using the exact same elements, okay? So you have 6 carbons, 20 hydrogens, and an oxygen, and you can hook that together multiple different ways. And when we hook those same atoms together in multiple ways, we call those isomers, okay? Now, there's different types of isomers, okay? The first one we want to talk about is called a structural or constitutional isomer. So a structural isomer would be one that has all the same functional groups, but it just has the substituents in different places, okay? Then we have constitutional isomers, which means we can have different functional groups, but all the same atom, okay? So that's the difference there. But what we're going to talk about in this particular chapter, and we talked about structural and constitutional isomers when we were doing nomenclature. Now, specifically, we're going to talk about stereoisomers. And stereoisomers have exactly the same connectivity. However, their arrangement in space is different. So if you can imagine you have 5 things hooked to something, and then you just swapped these 2 atoms, they are now different places in space, even though they have everything hooked together all the exact same way. Okay. So within stereoisomers, we have 2 subclasses of this, okay? The first one is called an enantiomer. An enantiomer, okay? And an enantiomer is a pair of compounds that look exactly the same if you look at them in the mirror. But when you try to overlap them, put them on top of each other, 2 of the atoms don't match up, okay? So exactly the same in a mirror, but when you try to line them up, they don't match up, okay? Now, so that's what we call enantiomers, and there's always 2 of them, okay? Diastereomers are when you have 2 or more stereoisomers in the same molecule, okay? And that means you can have different isomers based on the number of stereoisomers, stereocenters in your material. So anyway, these are the definitions we're going to go over today, and these are the ones we're going to define clearly and get those in your head. All right, so let's go ahead and talk just in general about isomers again. Again, we can have what we call those different isomers. So if we had just this C2H6O, okay, that's a very simple molecule. However, there's multiple ways in which we can fit them together. Now, one way we can fit these together is by going ahead and making it so there's an ether here. And with that ether there, that means that we have a carbon-oxygen carbon bond, and that this particular thing has a very low boiling point, and it doesn't have strong bonding. It only has dipole-dipole interactions. Okay. Now, if we were to just move this oxygen between those 2 carbons to between a carbon and a hydrogen, we end up with this compound here, ethanol. And ethanol is a liquid at room temperature, and it has the hydrogen out here so it can hydrogen bond. So it boils at a different thing. And in fact, it is very different in the way it interacts with the body. Dimethyl ether is very poorly soluble in blood and does not work very well in the body. However, ethanol is very soluble in the body, and some of us use it on a weekly basis. Insert laugh here. All right. So that's the difference between isomers. Okay. So in the idea of constitutional isomers means we have them hooked together in different ways. So for example, we can have it where this right here is a C5H12, which is a very simple compound. And if we drew it out straight, it would be this nice linear pentane here. But just by moving any carbon any other place, it becomes an isomer. And as we learned about the van der Waals forces, those are very weak forces. And the more linear they are, the more they can van der Waals force, and therefore it has a higher boiling point. Okay. Now, let's take a different isomer here. 4 carbons, 10 hydrogens, and an oxygen, but we're going to keep an alcohol on each of these compounds. When we do that, we can actually get a structure where we have all the methyl groups on the same carbon as that OH group, or we can have a more linear system, or we can have a completely linear system. And they change boiling point based on the ability of it to hydrogen bond with multiple other things. Now let's take this other one here. So in this constitutional isomer, we're actually changing the functional group, okay? By starting with our carbonyl here on our second carbon here, we have a ketone, okay? And it has van der Waals forces, but it also has a dipole-dipole moment, giving it its pretty good boiling point here. Just by moving this carbonyl over one carbon, but keeping that hydrogen on that carbon, we end up with changing the functional group. We turned it into an aldehyde, okay? And it has approximately the same dipole-dipole interactions. However, if we were to take that, break it apart, and turn it into this ring here, we now have, we only have a dipole-dipole interaction, and we have a different functional group. Now we have an ether, and we have a different isomer. Okay. So the idea here is that these are what we call constitutional isomers, meaning they're hooked, the same atoms are hooked in different ways, and the functional group can change. Okay. So in this could be done in any way. We can change where an oxygen substituent is. We can branch the alkyl chain. We can do any of these types of chains as long as we are, okay. Now, in the case of constitutional isomers, okay, that's different than the conformational isomers, okay? So in this case here, this is a constitutional isomer change because we've changed the location of a bond. We've moved this sigma bond from here to over here, and that has changed the connectivity, okay? This is a constitutional isomer. It has changed its connection. However, because we have the possibility of sigma bonds have free rotation, right? There's nothing inhibiting them. So we could draw this structure right here, which is equivalent to this structure here, right here. But all we have to do is do free rotation around this bond, and we can draw that exact same structure here. Notice all the same atoms are hooked to all the same atoms. All we've done is draw where that one place where that thing has freely rotated down, okay? These are conformational isomers, meaning they're the exact same molecule drawn two different ways. And so there's a possibility to do this. In fact, when we do our nomenclature, you have to kind of think about, well, if I rotate this one, that's going to give me the longer chain. Okay, so we saw that conformational change a lot when we looked at nomenclature of branched alkyl chains. Okay, so now let's get into something different. The stereoisomers. And the stereoisomers have a difference in space, okay? All the same atoms, the same types of bonds, but they have a different configuration in space, okay? So geometric isomers are the same molecular formula, but a different spatial rearrangement due to the rigidity of a molecule. In that previous one, the conformational, we had sigma bonds that can freely rotate. In this case, we have pi bonds. Pi bonds don't free rotate. We cannot rotate around this bond here. Because we cannot rotate around that bond, we'd have to break that bond to rotate it. We now have it fixed in space, okay? So that makes these geometric isomers because they do not have the free rotation that the conformational isomers have, okay? So in this case here, we can have all the same atoms. We have 2 hydrogens, 2 carbons, and 2 chlorines right here. And in this case, if the chlorines seem to be on the same side of that double bond, we have a specific configuration, and it has a specific boiling point, okay? And this boiling point is defined by its relationship with the other molecules in space. And as it turns out, because of the polarity, this molecule has a dipole moment or polarity going toward those chlorines because they are both electron withdrawing groups. Okay. Now, if we were to look at this and saw, okay, this chlorine's on one side and this chlorine's on the other side. So they have equal and opposite poles, which means it has a net dipole of 0 and our boiling point goes down. But the key thing here is that they're on opposite sides of that bond. When they're on that same side of the bond, look at this, it kind of forms a C here. We call those the cis configuration or same configuration, same side, okay? And when we have them going through this Z configuration, that's our trans configuration or opposite side. So we have our same side cis and our opposite sides trans in our geometric isomers. Now this is specifically found for things like double bonds with multiple things bound to it. Okay. So if you only have two things on your double bond, you can use cis and trans because it is not ambiguous, because in the case of this right here, you know cis means your two groups that aren't hydrogen, notice these are hydrogens, your two groups that aren't hydrogens are on the same side, therefore they're cis. In this other one, we have two hydrogens, and the two things that aren't hydrogens are on opposite side, therefore they're trans. But what do you do if you have more than just two things attached to the thing? You do not have those two hydrogens. If you don't have those two hydrogens, we have to be more precise about our nomenclature. And for the more precise about our nomenclature, we have what we call the E and Z configuration, which means we can take any double bond with three or more things attached and assign it to a specific isomer in space. Okay. All right. So that being said, we have some rules that go us along with this. Okay. So the first thing we need to think about is that in the case of something that would look kind of like trans, meaning the two highest priority groups, and I'll talk about in a minute, are on opposite sides of the double bond, we call that entgegen, or opposite, okay, or across in German, okay? If those two groups we decide are the highest priority are on the same side of the double bond, like in the cis configuration, we call that zusammen, okay? And the easiest way to remember that is zusammen has Z groups on Z and Xi, okay? So if they're on the same side, that gives us the zusammen or Z configuration. If they're across from each other, that's the entgegen, okay? Now let's talk about how we assign priority, okay? So when we assign priority, the first rule is look at the atomic number of the compound, okay? So you can look at your periodic table and you'll see that the atomic number for carbon is 6, okay? The atomic number for hydrogen is 1, okay? So it's the atomic number, not the atomic mass, okay? So if we look at our thing right here, we have, this is atomic number 9, okay? And as we just look down that chart, we have fluorine, chlorine, bromine, and iodine. So that means this is our lowest number. So we'll call this, our lowest number is 1, and then this is 2, and then this is 3, and this is 4, okay? So that's just going, that's the approximate order in which their numbers are going down on the periodic table, okay? So that being said, we have bromine here. And so bromine is lighter than iodine, okay? If we look at just splitting half the molecule in half, and we only look at one side first, and we see that of those two atoms, between the bromine and the iodine has the higher atomic number, okay? Bromine is 35, iodine is 53. So iodine is the highest atomic number. So what I'm gonna do is I'm gonna erase these numbers right here, and I'm going to circle this as our highest priority on that side of the double bond, okay? Now let's look at the other side of the double bond, okay? So if we look at this side of the double bond, we see we have fluorine and we have chlorine. And the fluorine has atomic number 9. Chlorine has the atomic number 17, okay? Again, if you had the periodic table, you could just go down that list and say, well, this is obviously higher numbers, but we have our numbers here. So between fluorine and chlorine, chlorine has the highest atomic number, therefore it's the highest priority. So I'm going to circle that one. Okay. So now we look at the two highest priority things we have, and we say, are they on the same side of the double bond? If they are on the same side, they're together on that side, and we call it Zusammen. If they were on opposite sides of the double bond, one was below the double bond and one was above the double bond, that would be our E configuration. So that means because our two highest priority things are there on that same side, it is Z, or Zusammen. So when we name this compound, we would start with the Z in front, saying that it is a stereoisomer, that it has the Z configuration because the two highest priority groups are on the same side of that double bond. Okay, so that's the first rule of the E and Z nomenclature system, is you go by atomic number. Okay, so the second rule is, if you go by atomic number and they're all the same, what do you do now? So if we look at this example here, we have on this one, we have a chlorine, a carbon, a carbon, a carbon, and a carbon. Okay, so that means all of the things attached to your double bond have atomic number 6. Okay, so you don't give up. What we do is we look for the next thing attached to it. Okay, so in the case of this carbon right here, let's start with that methyl group there. So we have the carbon, which has our atomic number 6, but it has 3 things attached to it. And all 3 of those things are hydrogens. Okay, and we're going to list those in decreasing atomic number. Okay, so hydrogen, they're all 1, so it's just 3 hydrogens. Okay, now let's look at this carbon here. Actually, let me change colors. Let me keep it blue here. So this carbon here is this carbon right here, and it has 2 hydrogens on it, okay? But it also has a carbon attached to it, okay? So that means we have a carbon and 2 hydrogens attached to this carbon here, okay? So we've assigned that that one is higher priority than this one, okay? Why? Okay. Remember, we're looking at each half of the molecule. So we're looking at just assigning the priority to this half of the molecule. We have 1 carbon with 3 hydrogens on it. We have 1 carbon with 1 carbon and 2 hydrogens on it. Having that higher atomic number attached to that carbon now makes it the higher priority. Even though they started with the same atomic number, the things attached to it count toward priority. Okay. So what that means is that this group is the higher priority group in this compound on that side of the molecule. Okay. Now let's look at the other side of the molecule and follow those exact same rules. Okay. So if we look at this side of the molecule here, let's start with this one up here. So we have a carbon attached to 1, 2, 3 carbons. All right, so let's list that. So if we look at that one, we have right here, carbon attached to 3 carbons. All right, great. That's probably going to be the highest priority, right? Well, let's look at the other one. So if we look at the other one, right here, we have a carbon attached to 3 carbons. Uh-oh, it's exactly the same. We've moved 1 carbon over from our double bond, and we have the same number. Then we look at what it's attached to that, and we still have the same number. So what do? We go 1 bond over again, okay? And if we go 1 bond over again on the bottom here, we have a carbon attached to hydrogens. All of these carbons, which were these carbons here, are all attached to hydrogens. Okay, so, all right, that's our starting point. So let's go back and look at the other one right here. So we have these 3 carbons right here that were this. Now let's see what are attached to them. This carbon is attached to a carbon, so we have to put that up here. Everything else is hydrogen. Okay, so that one little carbon 3 bonds over makes that group the higher priority. So that means this group is the higher priority because we followed it bond to bond to bond to bond to get it out. So the first rule is if atomic number defines it, you're done. The second rule, this is the second rule, if you have to, keep going out bonds until there's a difference, okay? But remember, the key here is you look at one side and assign priority to half of it. You look at the other side and assign priority to the other half, okay? Then, whichever side those two priority things are on is what it is. In this case, we have our highest priority here on the bottom on this side, and our highest priority here on the top on this side. So what does that mean about the configuration of this particular compound? So they are not on the same side, so they are across from each other, which makes them ingegen. So that means we put an E out in the front of our, oops, let me do it in black. We put an E is going to be defining the stereochemistry of this compound. Okay, so first rule, atomic number. Second rule, keep going out until there's a difference. Okay, there's a third rule. Okay. So the third rule comes into play when you are going out from the center and you have multiple bonds. Okay, so when you have a double bond or a carbonyl or a triple bond, you account those slightly differently. Okay, so what we're going to do is we're going to go ahead and dissect this molecule and follow all the rules. Follow rule 1 first, rule 2 second, and rule 3 third, and let's see where we end up. Okay, so again, we start by cutting our molecule in half, and we assign priority one side, and then we assign priority to the other side. Okay, so just looking at this side of the molecule, let's apply rule 1. Carbon, atomic number 6. Nitrogen, atomic number 7. Okay, so just in that first connection, using rule number 1, we've assigned priority to this side of the equation, with this side of the double bond. This is now our double bond. This is our highest priority on that side, okay? Do you see why? Okay, even though there's a whole bunch of other stuff going on there, we used rule number 1 first, and we could define a difference between the two groups. Therefore, we're done. Okay, let's go to the other side of the molecule now. So if we go to the other side of the molecule here, and let's look at this side now. So the first atom we go out there is a carbon with 2 hydrogens and a carbon with 2 hydrogens. Okay, so now we're gonna have to apply rule 2. So we had to go out one more. And now we have a carbon with a triple bond to nitrogen and a carbon with a double bond to oxygen. Okay, so now we have to apply rule 3. Okay, rule 3 states that if you have a double bond, that means you have to count the atom that is there for the sigma bond. You also have to count it for the double bond. So in the case of this atom right here, we have to count the sigma bond, so it's oxygen once. We have to count the double bond, oxygen twice, and the only other thing it's attached to is that carbon, okay? So that's how we define that particular group. Let's go ahead and define the other group. This is also rule number 3, okay? We have this carbon here, and it's bonded 3 times to nitrogen. So the first one is our sigma bond. The second one is our first pi bond. And the third one is our third pi bond, okay? So that means we have oxygen, oxygen, carbon is attached to that carbon. We have nitrogen, nitrogen, nitrogen attached to that carbon. Okay, now we have a difference, okay? Oxygen is atomic number 8. Nitrogen is atomic number 7. We have a difference between them now. We have something with a higher atomic number, and therefore it is assigned higher priority. So that means this group is the higher priority on this side. Okay, So now let's go back over here. We've assigned our highest priority to this side just from rule number 1. And we had to go through rule number 2 and rule number 3 to assign this as higher priority on this side of the molecule. So now, based on that, is it E or Z? Type in the group chat. Come on. A couple of different responses in the group chat. Come on. All right. Yeah, there we go. Good, good. Yes, yes. All right. So, and the reason is because they're across from each other from that double bond. They're on opposite sides of the double bond. So that makes them engagen, and therefore they are the E configuration. Now, I will unscribble over this thing right here, and I want to show you how we would note that. So notice we have brackets with a capital E, and if you type it, it should be italicized, and then dash the rest of the compound name, okay? So the stereoisomer assignment is always at the beginning of the system. The reason is that you need to know where the stereoisomers to help you draw it correctly. Now, the other cool thing about this stereoisomer is it is now completely unambiguous, okay? If I gave this name to somebody who knew their nomenclature, as you will soon, you would draw this exact compound in this exact configuration because this told you which side to put these two groups opposite each other. Okay? All right. So that's E and Z, and those are the 3 rules. So go ahead and write those 3 rules down. Atomic number first. If atomic number doesn't do it, what is it connected to? The highest atomic number on those wins. If that can't solve the problem, then you go and use the multiple bond rule, which is rule number 3. Each bond to an atom counts, okay? So for example, if we only had, if this was instead of the cyno group, we had an oxygen bonded to a carbon and bonded to a hydrogen here, okay? We have 2 oxygens here and only 1 oxygen here. That would maintain it still as higher priority. So the number of those higher priority groups can come into play. It's still rule number 3, but it's a subtle part of rule number 3. Okay, all right, so we are on time, great. All right, questions on that? E and Z. Again, if you only have 2 groups on your double bond, cis and trans is perfectly acceptable. And you can actually look at that is that cis will always be zusammen and trans will always be engagen. Okay, so if you end up, you know, wanting to be more precise, you can always use E and Z. It's always correct. However, cis and trans does work for things with 2 substitutions. If you only have 1 substitution on your double bond, the other 3 are hydrogens, there are no stereoisomers. Or there's no difference in them. Okay, questions on that. So that all has to do with stereochemistry around a double bond because that double bond cannot rotate. All right, I'm going to pause here for questions, and then we're going to go to the next one, the stereoisomers related to things with only sigma bonds. Okay, so let's talk about, you can have stereoisomers or fixed places in 3-dimensional space with just sigma bonds. And what we call these is, we call it a chiral center, or it's a special type of stereoisomerization called mirror image stereoisomerization. Meaning you have the same 4 things attached to a group, but if you looked at them in a mirror, they would look identical, and therefore they have mirror images of each other. However, to be true stereoisomers, you have to meet another requirement, okay? That when you take these 2 things that look exactly the same in the mirror and you overlap them, 2 of the atoms don't line up, okay? So that's what we call non-superimposable, okay? So they have to be mirror images of each other and non-superimposable, and only have sigma bonds. Okay. So there's also another requirement to always look for right here. And it's kind of subtle, but you have to have 4 different things attached to carbon. If you have any 2 that are the same, that means when you rotate them around, you can reorient them so those 2 things will line up. So the requirement is 4 different groups attached to a carbon. So if you wanted to say, hey, does this have stereochemistry? No, there's only 3 different groups on this thing and 2 hydrogens, therefore it's not. I don't have to worry about it. Okay, so that's the first thing you should always do whenever you try to look at a chiral system, or the chiral, which is the 4 different things bonded to. So let's talk a little bit more about, quote, chirality and this non-superimposable mirror image. Okay. So the idea here is that if you have these molecules and they look exactly the same in a mirror image, okay? So let's look right here for a little bit of a minute here. So if we had just this compound right here, and we wanted to figure out, does it have another compound that looks kind of like it in its mirror image? And can it be superimposable? The first thing we do is we draw an imaginary mirror. In this case, it's this line right here. And then we build out from that. So this bromine is the first thing we see. This bond is the second thing we see. This carbon is the third thing we see. This bond and this bond. See how these are all in exactly the same position. They're just mirror images of each other. The chlorine, remember the thick wedge like this means it's sticking out of the plane of the screen for us. So it's sticking out toward us to give us 3-dimensionality. It is sticking out toward us and it's still that chlorine. That dashed wedge right here indicates it's going behind the screen or behind the plane of the paper. Okay, so that hydrogen's going away from us. And we have that same thing over here. Okay, so using that simple test of going from the center out, you should be able to prove to yourself that these are definitely mirror images of each other. Okay. Now, are they chiral? So let's find out. First of all, does it meet the first rule of chirality? It meets the first rule of chirality. What's the first rule of chirality? We must have 4 different groups. So even though we can draw this as a mirror image of itself, we have 2 of the same group. We have 2 hydrogens, which means all we have to do is basically rotate this part down and this part up, and it'll look exactly like this molecule. Now, if we have something that can make a mirror image, but we can rotate the molecule around so they line up, we call this achiral or non-chiral. The A in front of the chiral stands for non-chiral, okay? So we have to look for this when we start looking at these things bonded to carbon to identify whether we have this chiral or achiral. So in the case of this particular molecule, it does have a mirror image. However, if we rotated this up and this bromine ended up coming back here and our chlorine stayed out front, it would be superimposable. Those 2 hydrogens would line up, the 2 bromines would line up, and the carbon would all line up, okay? So in another way to look at it is when we draw it in this configuration over here, so you can imagine just moving this compound on top of this. This chlorine is going to line up with that. The bromines are going to line up with, and these 2 hydrogens, this is going to line up with that hydrogen, this is going to line up. So because they can overlap each other, they are achiral or non-chiral. Okay, so that shows you the definitely 2 definitions for chirality. 4 different things, mirror image that's non-superimposable. Mirror image that's non-superimposable. Okay. So now we need to think about some other things associated with chirality. Okay. Within chirality, we have this thing called a plane of symmetry or a mirror plane. So a plane of symmetry is where you can slice either through the bonds or through parts of the molecule, and it'll look the same on both sides, as if you cut a mirror in between and it looked exactly the same before and after as when you cut it with a plane. Okay, so if you could imagine, it's just an imaginary place within the molecule. It usually lines up along bonds so that you can see it. So in this case here, we have our plane of symmetry cutting through this bromine, this chlorine, this carbon, and this chlorine right here. And when we do that, these hydrogens look exactly the same on both sides of that mirror. Okay? So in this configuration here, it looks like that this one is going backwards, but remember, we're looking at the plane of symmetry, meaning its mirror image is going to make it look like it's going back. So because it has this plane of symmetry in it, because these two things will look exactly the same if we cut through the molecule, it cannot be chiral. It must be achiral. Okay. So notice that a lot of times these planes of symmetry will go through 3 bonds. Sometimes it will actually go through the middle of bonds. So like when we start doing rings and other things, it actually might start cutting through like in between atoms. So you have to look for your planes of symmetry in various places. Okay. But again, this plane of symmetry comes up from the fact that we have 2 of the same groups. And when we have a total 2 of the same groups on that same carbon, it must be achiral. All right, questions about the definition of chirality? Okay. So once we define a compound as chiral, we now know that when we have chirality, you can get the image, the original image, and then its mirror image. And because they have the groups that are in different places, they are not the same thing. So all chiral compounds have a mirror image, and that pair of the 2 compounds are called enantiomers. So it's that pair, or the pair of enantiomers. Okay. So let's look at this compound here and decide whether or not it has a stereocenter. I say it does, but let's prove it. Okay. We have a hydrogen, a fluorine, a bromine, and a chlorine. 4 different groups. Okay, so that follows number 1. And let's look at number 2. Number 2 is non-superimposable mirror image. Okay, so if we look at here, let's go ahead and draw our plane. Make sure that this is a mirror image for us. Right here. So the bromine's here, the carbon's there, the fluorine's there, the chlorine's sticking out at us with this solid wedge, and the hydrogen sticking back with that dashed wedge. Okay, so because of this orientation, the fact that they do go from the middle out and match identically, those are mirror images. Okay, so we've proved to ourselves they have 4 things and they are mirror images. Okay, and because they have 4 things, they can now not be superimposable, and therefore this bromochlorofluoromethane is chiral. It has a mirror image. It's non-superimposable, meaning we have 2 possible different compounds in 3-dimensional space. Okay? And that pair of those 2 compounds that are only different in 3-dimensional space are called the enantiomers. And therefore, that makes us have our chiral center is the one in the middle. The chiral center, or the one that holds the chirality, is, come on, the carbon that all 4 of those different groups are what we call the stereocenter. Sometimes it's called the chiral carbon. Sometimes it's called the asymmetric atom. I think I'll use probably the chiral carbon or stereocenter most. But stereocenter is the carbon that has those 4 other things bonded to it. Okay, and because of that, that's the one we have to actually start with and know where it is and the four things attached to it to help us identify what isomer we have. Okay. So any molecule with a stereocenter or four different groups on it will always be chiral. Okay. Questions on that? So we have chirality is the definition of having something with non-superimposable mirror images. Our chiral centers are the carbon with those four different things attached. And that pair of mirror images that are non-superimposable are enantiomers. Okay, so one of the reasons this is so important is that there's a lot of different opportunities to have chiral compounds. Okay? And a lot of them found in nature are very interesting because the body can only process one of the two isomers. For example, ibuprofen, very common, only one of the two stereoisomers is actually biologically active. If you look at naproxen, which is another one, they have two stereoisomers. One is actually a liver toxin, the other one is an anti-inflammatory. Okay? So one of the classical cases of this was this compound called thalidomide, right here. And in the 1950s, they used to give thalidomide to pregnant women because to ease morning sickness. Okay? And what they found out was that they were giving them a mixture of the R and the S. They had not separated this out, and they did not know which one was actually active. So they would give a mixture of R and S, and so the S portion would act as a sedative and calm their morning sickness. The R turned out to be a teratogen or cause massive birth defects. So there's like thousands of children born with birth defects because of this other isomer. Years later, when they finally figured this out and they only sold the S, they still had no customers because nobody could trust it. Nobody understood that R and the S was the control. So which isomer you have is very important, and identifying them is very important as well. The other thing, which is really cool, is this is a common terpene. We call it a terpene because it has a couple double bonds and it's naturally occurring. But it's funny that the S, which is the limonene, S-limonene, actually smells like lemons, but the R-limonene reacts differently in our nose and it smells like orange. So that's a less dramatic difference on there. There's also carbone, where one smells like caraway seeds and the other one smells like mint. So this is very common throughout the natural world. The R and S is very important. Okay, so this is about 1050. This is about where I wanted to stop. And then we're going to continue on next time with definitions of what is R and what is S, the prioritization, and how to label these correctly. Okay? So let's go ahead and I'm going to go ahead and stop recording, and you can hang out for questions if you want.